Hi, my name is Ankita. Today I'll explain my solutions for task 2.1p. The task majorly focuses on the graph algorithms, graph traversal, shortest path, connectivity, negative weight cycles, and so on. So in part 1, where Miss Maple wants to choose a hotel that has a maximum number of shortest path from the train station. Since every edge in the graph has the same weight of 1, the most suitable algorithm is breadth first search or BFS. The algorithm keeps two pieces of information for each node, the shortest distance from the source node and the number of shortest path leading to that node. Initially, every distance is set to infinity, every path count is set to 0, and the source node has distance 0 and the path count 1. During BFS, when the node is discovered for first time, its distance is updated and it inherits the path count of its parent. If another path reaches the same node, the same shortest distance, we add the parent path to the current count. So during BFS, the runtime complexity becomes O(n plus m) because every vertex and every edge is processed once. Now we go to part B, where it has asked us to determine whether the communication network is connected or not. So I have used the depth first search or DFS. So for step by step, I first selected the node and then we ran the DFS and marked all the visited nodes. After traversal, we checked whether all the nodes are visited or not, and if the node was visited, the graph is connected. And if any node remains unvisited, then there is no path to that node, means the graph is disconnected. The runtime complexity is O(n plus m) because DFS visits every vertex once and every edge once. Then for part C, where we have to use adjacency matrix, normally DFS with the adjacency. So now we go to part C. So part C, we have used the DFS using the adjacency matrix. Normally with that matrix, it runs O(n plus m) times. But however, with the matrix which is used, DFS must inspect every entry in each row to find neighboring nodes. Since there are n rows and each row remains n entries, the complexity becomes O(n square. Then we go to part D, where we have to do the algorithm. So in part D, I have converted the adjacency matrix into a directed weighted graph and applied the algorithm starting from node 1. The directed edges include 1 to 2 with weight 4, 1 to 6 with weight 10, 2 to 4 with weight 5, 2 to 5 with weight 11, and the remaining edges shown in the report. After executing the algorithm, the order of the node removal from the priority queue was 1, 2, 4, 3, 6, 7, 5, 8, 10. Node 9 was unreachable from node 1. So the shortest distances were node 1 is equal to 0, node 2, 4, node 3 equals to 11, and so on, while node 9 remains unreachable. In part E, I have increased all the edges weight by 1. So the answer is no. So when every edge gains an extra cost of 1, path containing more edges receive a higher increase than the total weight. So as a result, the path that was previously shortest may become more expensive than another containing fewer edges. Part F, negative weight cycle. In part F, the graph contains exactly one negative weight cycle and the vertices of the cycle are already known. So to determine whether there exists a negative weight path from a source, node S to destination node T, I performed two reachability checks. First was DFS, or we can use BFS also from the source node, that check whether the cycle is negative cycle is reachable or not. And secondly, after starting the DFS from the vertex in the negative cycle, we have to check whether the destination node is reachable or not. So if both the conditions come true, the source can reach the negative cycle, otherwise the source can reach the destination. Then a negative weight path exists because the cycle can be traversed repeatedly to reduce the total path costs indefinitely. And the runtime complexity for that is O(n plus m), again because only two graph traversals are required. Thank you.